All right, so this screencast is about the Michelson Interferometer Lab. And in this lab, we used a Michelson interferometer not to determine the wavelength of a laser beam, but more so in order to determine the relationship between pressure and the index of refraction. So pressure of air versus index of refraction. We already know the wavelength going in, which is 632.8 nanometers. It's just that now it's what's that relationship? So we're looking at interference patterns and what are various fringes. A wave of light is kind of like a droplet of water, we'll say, and we're passing by and we're watching the ripples pass us by, which evokes images of summer, which I really want to take part on because I'm sick of this lab writing. But anyway, back to the lab, which I love. So we got the center of the fringe, center of or the bright spot, or in the center, and then and there's a pass along. So there's a fringe, another fringe, another fringe, and each of these are and that is what happens when we have two waves are interfering, which is what an interferometer gives you is interference. So as seen in the in this diagram here, this is kind of what we use for our lab. We had light, and we had a beam splitter. So some of it reflected downwards towards a mirror, and that was that was the adjustable one, which created a gap of distance d. And for this lab, what that distance was did not matter. We just adjusted it. Until we had interference patterns was all we had to do. And then but right here that was a gas chamber or an air chamber, and it varies the pressure inside, which affects and by varying the number of the pressure that goes through, what it does is that it affects it affects the wavelength of light, ultimately. And then there's a relationship I'll talk about below. The rest of it, and it's important to note that the light that goes down to this path, it actually it goes through this chamber twice. Anyway, then we have the light passes through the beam splitter, and then it bounces off a mirror, and then in the end, it all kind of goes onto a screen. Well, actually, it doesn't all go on, but about equal amounts from either traveling either path gets on the screen. So anyway, so then we are given the relationship between wavelength pressurized under pressure is equal to wavelength of the air vacuum, which we know is 1. Divide that by the index of refraction. M is the number of wavelengths that are passing through, and the relationship there that between that number of the number of wavelengths of light in this chamber is 2L. I'm labeling that L. Divide that by a lambda, and the reason it's 2 is because it passes through back and forth 2 times before it hits our screen. So anyway, lambda pressurized, we'll call it, is oh, I've got that up there again. Is that, and then we can just do some substitution. M, number of wavelengths, is 2L n over lambda vacuum, which is 632.8. Fringes occur when there's destructive interference, and then bright spots occur when there's constructive. And every fringe occurs at a wavelength apart, so the fringes equal 2ln, divide that by lambda vacuum, and then we can find a relationship here between dn. So dn, so the change in n is lambda vacuum times the change number of fringes, because we're actually not getting in this lab, we did not actually necessarily know where the bright spot was, and similarly with the pressure measurement, we didn't necessarily know precisely. We didn't necessarily have a zero, but we certainly could. We know what the zero is, um, which which is 1.029, and then atmospheres for vacuum. But anyway, so the change in that is the relationship between is the change in fringes times lambda in vacuum. Divide that by 2L, which is the optical pathway. So anyway, there's some pictures we took of what we looked like, and okay. So in this one, there's the optical chamber. So basically, you've got light that, well, and this shows it well, maybe not so well. Let's enlarge that. So we got the laser there. It's bouncing off a mirror, another mirror right there. There we go. And then it goes, and then it lands right here onto the beam splitter. Some of it goes through the optical chamber. That's that red thing right there, and then back, and then we have this. And it lands on a screen, which we don't, which it'd be that guy right there. Yep, yes, that would be it. The bright spot there. So anyway, and you can see a big bright spot there in the middle, and then we're beginning to get maybe some few fringes around there. We found that our optical path is 74.5 millimeters. Our lambda in vacuum, as I've said, is 632.8 nanometers. So how do I do data analysis? Well, data analysis is that, so basically what we're doing is we have to take this, we're comparing index of refraction to pressure, and using the fringes to do that. So I've got data right there, and let me pull that over. There we go. So first of all, so we know at pressure of 0, index of refraction is 1.0029. However, we also know that that drops then as we increase pressure. So anyway, so fringes are so the number of fringes through an equation give us the allow us to find it allows us to find our dn, and that was that right there. So pressure dn, and then n is just 1.0029 minus dn. I plotted that here just quickly in Excel, and what we find is a pretty linear relationship between them, with a slope of 2 times 10 to the 5. And then we also want that was for the way back down, and the way back up we had 3 times 10 to the negative 5 would be which is the slope of change in pressure, change in index of refraction to change in pressure, so that's the relationship there. So it is indeed a linear relationship.